Hello, in this video I'm going to run through the basics of the Doppler effect. So this is the change in the apparent wavelength of a wave due to the motion of the source of that wave relative to the observer of the wave. And this was first set out by Christian Doppler in the 19th century in 1842. He was an Austrian physicist, and of course in the 19th century waves were very much in vogue, so a lot of people were studying them, and he was the first one to really lay out and describe this effect in detail. So I'm going to run through the basics in a three-stage diagram, and then we can start doing a little bit of the basic maths behind simplified uses of the Doppler effect. So I'm going to set up two observers here, one on the left, one on the right. So two eyeballs staring at a source that's in the middle. And going forwards in time, top to bottom here, I'm going to have the same two observers observing the same source. And I'm going to set this source off to move into the right, towards the observer on the right. So at time t equals 0 at the beginning, it's going to release its first wavefront. So this is the start of the first pulse, which is being sent off to both observers. So this wave is going to propagate both left and right, although the source itself is moving to the right. So if we go down, so if that's at t equals 0, if we go to t equals t, the period of oscillation of this particular wave, it would have moved to the next wavefront. We would have gone through one oscillation, we're going to get the next wavefront. This has propagated in both directions. So let's move one wavefront off to the right and the same distance off to the left. Now, if the source was static, this is just what we'd get. You know, this distance here, this distance would be the wavelength, and we got a static source, and that is the wavelength that will be observed by both observers. But I'm setting this off with some speed v off towards the observer on the right, so that's not going to be the wavelength that these observers actually see. Let's go, actually at this point then, let's add in the next wavefront. We've gone through one period of oscillation. The source has now moved to say here, and now it is going to release the next wavefront. So you can already see what's happening here, but I'm going to go through this for another cycle. Let's go to 2t. So the red wave has now moved again out to here and here. The blue wave has done a similar thing. So that's now moved through a wavelength to say here and another one to say there. Now the source has moved again to there, releases the next wavefront. Right, so you can see what's happening in terms of the apparent wavelength here. If you're off to the left and the source is moving away, your apparent wavelength is much larger than it is if you're off to the right and the source is moving towards. So two different apparent wavelengths depending on whether the source is moving away or whether it's moving towards. Here we've got the shorter wavelength if it's moving towards. If it's moving away, we've got the longer wavelength. Longer wavelength means a red shift. Shorter wavelength means a blue shift. And you often hear about red shifts and blue shifts in astrophysics when people are describing how objects are moving relative to the Earth. You know, they talk about red shifts if it's moving away, blue shifts if it's moving towards. And this could be lots of different things. You know, this could be galaxies that are moving away due to the actual expansion of the universe, so the space itself expanding, and that is creating a similar effect. Okay, it's not a proper motion of the source, it's not the source moving through space, as I've spoken about in this particular example, but the effect is the same, and this is why we're still using the Doppler effect. You know, space itself expands, and that makes things move further apart, so we get the same outcome. It could be actual motion, actual proper motion of objects. You know, it could be a star that's moving around. It could be the rotation of a galaxy. If you've got a spiral galaxy that is rotating and we're looking into the plane of that rotation, we're going to have some parts of the galaxy moving towards us and some parts moving away. So we're going to get red shift and blue shift. blue shift for the bit moving towards, red shift for the bits moving away. So if you then look at the spectrum that would be produced by that galaxy, you're not going to be getting sharp absorption lines or sharp emission lines. These absorption lines are going to be spread out because some of the wavelengths are going to longer wavelengths because of the red shift, and some are going to shorter wavelengths because of the blue shift. So when you're looking at the spectrum of an object in the night sky, when you're seeing broad emission lines and broad absorption lines, then you're looking at a lot of motion in the, well, whatever it is that object actually is, whether it's in the atmosphere of a star, whether it's the motion of the galaxy. So yes, you've got all of that going on. So that's giving us a lot of information. And this is what we're doing. We're taking spectra and we're looking at lines and comparing them to what we measure in the lab. So if we look at a particular wavelength, a particular energy transition between two energy levels in an atom, and we get a measurement of the wavelength in the lab, so for a static source, we can then compare that wavelength to the same spectral line in a spectrum of a galaxy or a star. So obviously this raises the question of, well, how do you match them up? How do you know that the spectral line that you've measured in the lab is the spectral line that you're looking at in the spectrum of the object in the sky that is moving? Because all of the wavelengths are changing if you've got this relative motion. So you need to have some way of matching up the wavelength of the static source with the wavelength, the apparent wavelength from the moving source. And sometimes this is quite tricky. I mean, in the past, people really got caught out by this because, well, it was a new science. And some of the redshifts can be very large, so large that people didn't actually think they could be the same line. So, yeah, you've got things like that happening. I also mentioned this in things like planetary nebulae, where you get forbidden lines. So you might get new transitions, new energy level transitions that we're just not used to getting on Earth in the lab. So, sometimes you'll get an unusual line, a forbidden line in a stellar spectrum or something like that, or a spectrum of a planetary nebula. But there are ways of matching these things up. People have got much more adept at this with more and more observations. You get sets of lines as well. So you get things like the Balmer series. So this is the Balmer series of hydrogen, which are 6 spectral lines of hydrogen. 4 of them are in the visible range. And one of them, the 5th one, you can see with the naked eye, but it's classified as being UV. And then there's a 6th one. And they're at wavelengths that people become quite familiar with when they spend some time in astronomy. So you've got 656 nanometers is the first one in the series, which is referred to as H alpha. So these go H alpha, H beta, H gamma, H delta, etc., down to 6 of them. So this is H alpha is at 656 nanometers. Then you've got H beta at 486, H gamma is 434, H delta is at 410. Must say my memory goes after that of what the others are. But I do tend to remember the 4 that are in the visible range. And these are all talking about transitions, energy transitions of hydrogen going down to and from the second energy level. So n equals 2, not ground state, n equals 1, but in and out of n equals 2. So for H alpha, this is 3 to 2. So transitions from hydrogen energy level 3 to 2, or from 2 to 3, are all at 656 nanometers. And then H beta is 4 to 2, and then 5 to 2 for H gamma, 6 to 2. We're just going to a different energy level each time. And H alpha is something that you hear about a lot in astronomy. And if you're looking at equipment as well, you're looking at telescopes, you might look at a solar telescope, which might be described as an H alpha telescope. So that is allowing light of wavelength 656 nanometers with a certain bandwidth. So you've got a certain plus or minus on that, and it's letting through light at that wavelength. you can buy H alpha filters that you can put on regular telescopes as well in order to observe the sun and get maybe a little bit more resolution, a better view of it. So that's what's happening with those. And because these are at fixed intervals, when you've got a set of them at certain wavelengths, where you can, sometimes match up the whole set with the spectrum that you're looking at, and then say, okay, right, these ones are now all lining up. So I've now got what the shift is in all of these wavelengths. I've got my delta lambda, my change in wavelength for this particular object. Because if you're matching 6 of them, or even a subset of these 6, it's so much easier to do than just match one line. Right then, so to wrap up with all of this then, let's look at the calculations that we do around all of this. And we use a simplified, non-relativistic version of the Doppler effect for the calculations. And we're given this pretty much, where we have this delta lambda, so the change in the wavelength divided by the wavelength from the static source, is roughly equal to the velocity, so this radial velocity of the object divided by the speed of light. And this is for v being much less than c. So this is non-relativistic. We can also replace the wavelength here with frequency if we wanted. So we could have change in frequency over frequency of the static source. But we seem to spend more time doing calculations based on wavelength rather than frequency. Spectrums that we're setting up, these have got wavelengths along the x-axis, so it makes sense to use the wavelength version. So let's take a little bit of a closer look at this then. Doing a basic version of this isn't particularly complicated. We've got our basic wave equation, so we've got our, for electromagnetic waves is what I'm looking at here, so our speed of light, that's our frequency times our wavelength. Or we could write this as our wavelength is the speed of light multiplied by the period. So we're going to get maybe a little bit more, well, we'll use both of these, but we get more mileage out of the second one here. So we've got our source, which if it's static, then we're just sending out these pulses. We've got these wave fronts propagating out to the right here, and we're going to say that the wavelength is c times t, exactly as I've said here. So if we've got a moving source, so this is for static, if we've now got velocity v, velocity equals v, we start off and we send out the first wavefront. So that's going to be this one, which is saying got to here. But rather than sending out the second wavefront when we're at the same location, the source has now moved. So it's moved over here when the second one comes out. So what we end up seeing for this apparent wavelength, so that is our apparent wavelength here, that is going to be equal to c times t. So that's the full wavelength as we had for the static source, minus this bit, minus, and that is going to be v times t, because in time t, the source has moved v times t. That's just our velocity times time gives us a distance. So that gives us our apparent wavelength. So this is c minus v multiplied by t. Not that we really need to write it that way, because we're going to get our change in wavelength is the original wavelength minus the apparent wavelength. That is the difference. That is what's changed. So that is ct minus ct minus vt. So that just leaves us with vt, which is v lambda over c. Just going back to our definition of what t is. We've replaced this, well, we've taken that and subbed it back in. We've taken vt and said, okay, well, t from this equation here is lambda divided by c. So there we go. We then divide through by lambda and we get delta lambda over lambda is equal to v over c. And that is in the case where v is much less than c. The less it's moving, the closer this moves to an actual equality rather than an approximation. So this is for non-relativistic. I always find it hard to say that. Non-relativistic motion. Yeah, we can do a similar thing for frequency, but we know from this anyway that we're getting a relationship here. We've just been able to sub one out for the other, but we can go through the same process here and get the same outcome for frequency. And this is the calculation that we do a lot. We don't have a lot of calculations that we do in this section anyway in astronomy and cosmology. So they really batter this one in exam questions if they want some calculations done. The only thing you have to be careful of is making sure you get the right lambda. It's easy to work out the change in the wavelength because we're given two wavelengths. So, that's fine. We're just working out the difference. But in terms of lambda, we need to have the wavelength of the static source. So when they say things like H alpha in the lab is 656.4 nanometers, and the wavelength that we observe in the spectrum, like, let's say that had moved to, I don't know, 658 nanometers. So we've got a little bit of redshift going on here because the wavelength has gone up. Then we're saying the change in the wavelength, fine, that is 1.6 nanometers. But the wavelength we want to use in the formula on a denominator is for the static source. So lambda is the 656.4 nanometers. And you don't, if you've got everything in nanometers, you don't need to put into the calculator your 10 to the minus 9 because these are just going to cancel. The thing here on the left of this equation doesn't have any units in it, so we can just do 1.6 divided by 656.4. Simple as that. You don't have to worry about the nanometer bit. And then we can work out, multiply that by c, and you get the velocity, the radial velocity of this object, the speed at which it's moving away from us. And that's what's causing that Doppler shift. So there you go. I mean, it's not the most complicated of topics. A lot of this you've probably already covered and you're probably familiar with. But it's useful just having that little bit more context, how we come up with this equation, things about Balmer lines, and how we can match up spectral lines in the lab with spectral lines that we see on spectra that we've actually recorded. So there you go, Doppler effect.